What if you could see inside the human body, charting the intricate pathways of the brain, or spotting a tiny tear in a ligament, all without a single cut and without using any harmful radiation? It sounds like science fiction, but it's the reality of magnetic resonance imaging, or MRI. To a patient, it might just feel like lying in a noisy, narrow tube. But what's actually happening inside that machine is a breathtaking application of physics, turning the tiniest particles in your body into a detailed map of your inner self. Today, we're going to unravel the science behind this medical marvel, from the quantum spin of a single proton to the complex code that builds the final picture. At the heart of it all is the most common element in your body: hydrogen. About 60% of our body is water, and every water molecule has 2 hydrogen atoms. This makes hydrogen a perfect target, but we're not interested in the whole atom, just its nucleus, which for hydrogen is a single proton. Now, this proton has a fascinating quantum property called spin. You can imagine each proton as a microscopic spinning magnet, like a tiny compass needle. Normally, the billions upon billions of these proton magnets in your body are all pointing in random directions. Their magnetic fields cancel each other out, so there's no overall magnetic effect. That's where the giant magnet in the MRI machine comes in. This is the magnetic part of MRI. When a patient is moved into the scanner, they are placed inside an incredibly powerful magnetic field, thousands of times stronger than the Earth's magnetic field. This main field is called B0. This immense force does something remarkable. It makes the tiny proton magnets snap to attention. They are forced to align with this powerful field. Most align parallel to it, which is a low-energy state, while a few align in the opposite, anti-parallel direction, which is a high-energy state. This tiny excess of protons, pointing in the parallel low-energy direction, is what creates the faint magnetic signal that MRI is built upon. But they don't just align. They also start to wobble or precess around the axis of the main magnetic field. Imagine a spinning top wobbling as it slows down. It's a very similar motion. The speed of this wobble, called the Larmor frequency, is directly proportional to the strength of the magnetic field. This relationship is a cornerstone of MRI. So we have protons aligned and wobbling at a specific frequency. The next step is to get a signal out of them. This is where the resonance in MRI comes from. The machine sends a pulse of radio waves into the body using something called a radio frequency, or RF, coil. The key is that this radio wave is tuned to the exact Larmor frequency of the protons. When the frequencies match, resonance occurs. The protons absorb the energy from this RF pulse. This energy does 2 critical things. First, it knocks the spinning protons out of alignment with the main magnetic field, pushing them into a different plane. Second, it forces all these wobbling protons to sync up and spin in phase with each other, like a group of synchronized swimmers. Once the RF pulse is turned off, the show really begins. The protons start to relax, releasing the energy they just absorbed. As they do, they emit a faint radio signal of their own, which is picked up by the RF coil acting as an antenna. This process is called relaxation, and it happens in 2 different ways at the same time, which is the secret to MRI's amazing images. The first way is T1 relaxation. This describes how quickly the protons give up their extra energy and realign with the main magnetic field. Different tissues release this energy and realign at different rates. For instance, protons in fat have a short T1 time. They relax and realign very quickly. Protons in water or spinal fluid have a long T1 time. They take much longer to realign. The second way is T2 relaxation. This describes how quickly the protons, which were all spinning in sync, fall out of phase with each other. This dephasing is caused by the protons interacting with the tiny magnetic fields of their neighbors. Protons in water-based fluids, like in the brain or spinal cord, have long T2 times. meaning they stay in sync for longer. Protons in more solid tissues have short T2 times and dephase quickly. These different relaxation times, T1 and T2, are the magic keys to creating image contrast. By carefully timing the radio frequency pulses, and when we listen for the returning signal, we can create images that highlight these differences. This is done using a pulse sequence. To create what's called a T1 weighted image, operators use a short time between RF pulses. This doesn't give tissues with long T1 times, like water, enough time to fully realign. As a result, they produce a weak signal and appear dark. Tissues with short T1 times, like fat, realign quickly, give a strong signal, and appear bright. T1 images are fantastic for showing clear anatomical structures. To create a T2 weighted image, a long time is used between RF pulses and a long time before listening to the signal. This makes T1 differences less important. Now, the contrast comes from how long the protons stay in sync. Tissues with long T2 times, like water or fluid from an injury or disease, will still have a strong signal and will appear bright. Tissues with short T2 times will have lost their signal and will appear dark. This makes T2 images incredibly sensitive for spotting pathology, since many diseases involve inflammation and increased water content. There's also a third type called a proton density or PD weighted image, which basically just shows how many protons are in a tissue, giving a different kind of contrast. So we can get a signal and we can create contrast. But how does the machine know where that signal is coming from in the body? This is where the loud banging and knocking noises of an MRI scan come from. Those sounds are made by powerful gradient coils, which are secondary magnets that can be switched on and off very rapidly. These gradients slightly and very precisely alter the main magnetic field. First, to select a slice of the body, a gradient is applied from head to toe. This makes the Larmor frequency of protons vary depending on their position. The machine then sends out an RF pulse with a very specific frequency that will only excite the protons within the desired slice. It's like tuning a radio to a single station. Once a slice is selected, a second gradient, the frequency encoding gradient, is applied from left to right while the signal is being measured. This makes the protons on the left wobble at a different speed than the protons on the right. The frequency of the returning signal now directly tells the machine the left to right position of the signal. Finally, to figure out the front to back position, a third gradient, the phase encoding gradient, is applied. This briefly alters the wobble of the protons, causing them to accumulate a different amount of phase shift depending on their position. This process is repeated hundreds of times, with a slightly different phase encoding gradient each time, to gather all the necessary information to build the image. All this raw signal data, full of frequency and phase information, isn't a picture yet. It's stored in a temporary mathematical grid called K-space. You can think of K-space as the raw data negative of a photograph. The center of K-space holds information about the overall image contrast, while the outer edges hold the fine details and edges. Once K-space is full, a powerful computer applies a mathematical operation called a Fourier transform. This is the final step that converts the frequency data in K-space into the detailed anatomical image we can all recognize. While the physics is complex, the technology has been harnessed to create a suite of powerful diagnostic tools that go far beyond simple anatomy. For example, functional MRI, or fMRI, can actually map brain activity. It works by detecting changes in blood flow. When a part of the brain is active, it needs more oxygen. And fMR, I can see the magnetic difference between oxygenated and deoxygenated blood. This allows scientists to watch the brain think. Magnetic resonance angiography, or MRA, is used to get clear pictures of blood vessels, perfect for finding aneurysms or blockages. And diffusion-weighted imaging, or DWI, is an incredible technique that measures the random motion of water molecules. This is extremely useful for detecting a stroke within minutes of it happening, as the stroke restricts water motion in the affected brain tissue. Thanks to its incredible soft tissue detail, MRI is the gold standard for imaging the brain and spinal cord, for diagnosing sports injuries like torn ligaments in the knee, and for detecting and monitoring many types of cancer. And it does all of this safely. The main risk is the powerful magnet itself, which is why screening for any metal in or on the body is so critical. The loud noise is managed with ear protection, and for those who feel claustrophobic, there are open MRI designs available. The journey of MRI from a physics concept in the 1940s to a clinical reality in the 1980s is a story of incredible scientific achievement, earning its inventors a Nobel Prize. And the story isn't over. Researchers are now developing ultra-high field magnets for even clearer images, integrating artificial intelligence to help analyze scans faster and more accurately, and creating hybrid machines like PET MRI scanners. MRI is a true triumph of science. By manipulating the quantum properties of the most common atoms in our body, we've created an unprecedented, non-invasive window into our own biology, a tool that continues to save lives and deepen our understanding of the human body every single day.